We were trying to predict that, right? So that's where you will use a machine learning system. So machine learning system is nothing but it tries to discover a pattern and use that knowledge to predict what can happen in the future. Whether that prediction will be true or not, it's anybody's guess. That's what evaluation is for. So does it answer to your question? Yeah. Okay.
So based on the data, you can use different types of tools, because in the previous slide you did mention that if you're having more numerical data,
Yeah.
then you use one type of
Correct.
one product. Right?
Correct. You can use any kind of algorithm, but in my limited experience, I saw that when I did performance evaluation tests against systems, then for numerical data I found, especially when the data size is smaller and you are only working with numerical data, random forest used to work very well. Whereas if you work with huge amount of data and the data contains textual data, text kind of data like natural language processing or blog entry and things like that, then stochastic gradient descent work very well. And if you have moderate amount of data and it's not scaling that much, naive Bayes also kind of work, because these are the most algorithms. I worked with neural networks much earlier, like self-organizing maps, neural networks, fuzzy logic, but it was like long time back when I was studying PhD and I got kicked out of that program anyway because I was not doing very well. So hence I don't know much about it. My professors were very unhappy with this.
What is OCR and HWR?
It is optical character recognition. Like OCR fonts nowadays, you put it and they have image recognition. They can see what you have written. So that's the optical. HWR, I don't know. I just copied this slide.
And
Yeah, go ahead.
what cluster falls, for example, weather forecast?
Yeah.
In which area?
So weather forecast I will also say it will go with like inputs as big as like at least 10 to the power 3, and the data set size will also go high. It will be also very high because whether it's a very good question, you want to have air pressure, temperature, dust particles, seasonal change, cloud formation, I mean humidity. I don't even know so many things. Like these are all like different features for data prediction. I mean weather prediction. Yeah, so it will be very high in number. So these are some common things that came to my mind, but of course it is 10 to the power 3, so I cannot spell all of them. There are like so many features. So that would come there as well.
Where do you see social data coming?
Social data actually is not that big. Actually, social data will probably come to maybe about 1,000 features. I think it should be somewhere around there. In, text categorization. Yeah, see that's text categorization in social data. Probably see it's between 10 to the power 3 to 10 to the power 5. But whatever I have used the classifier from text, I found like even if it was not even coming to. So there are two kind of answers I'll give here. So if you know what are the key features that you want to use to build a textual model, then your number of features might be only 10 to the power 3 within that range, or you already know. But suppose you just bring in the data, whatever you gather from the social, and say every word that comes in is a feature by itself, then it will easily become 10 to the power 6 and above. You getting my point? So here the accuracy will be very, very like kind of shaky because you're letting the system decide what it is and all. And in the previous case, you are identifying which are the key features I want to determine the data on. So it can vary. Does it answer your question?
So when you talk about the y-axis, the training examples the data, like the way he said,
Yeah.
weather prediction, right? For weather, we have been capturing the data for a long, long time. So we basically have a real data to just run the model against.
Sure.
Okay, that's what you mean.
Sure. Yeah, that's the example. So a training data set will look like, so suppose in a email spam, the previous example that we said. So the first column would be spam, no spam, spam, no spam. That's the first column. That's the only label it will have. And the row would have content of the email, the IP address, the sender name. These will be the features, right? So these are the attributes or the features. So if you will in a database, the first column is your label that you want to guess or predict, and all the rest of the columns are the input, right? The features. And the more these rows you have, the better predictability you have. If you have very limited amount of data, then not so much. So that's what this thing is.
Are you saying that with let's say 10 of the power 4 examples with X, I'll be able to build a good text visualization model?
I mean, this is just a kind of a blueprint. It doesn't mean anything. This is just for showing purposes. each and every model, each and every thing, it requires domain expertise. It requires good choosing of the better algorithm underneath, and how knowledgeable the person who is using these systems are. So it's very hard to say one way or the other that whether this many. Just a rule of thumb, I was talking to another person from Facebook, and I asked him like, how do you determine how many examples should I use to train my model? And he just said, okay, if you are thinking the number of features you have is 2, then maybe 10 samples is good amount sample to predict it. If you have 3 features, then maybe 16 samples is good. So 2 to the power whatever the number plus 1. He was giving me this kind of logic. So maybe if you use that,
2 to the power and plus 1.
yeah, something like that. I don't know how he came out with it, but that's what he said. Yeah, go ahead.
So inputs is categories, so factors, right?
Factors, yeah,
Factors.
features, factors,
But
categories.
from statistical analysis, as I remember, it makes sense to take into account only orthogonal
Yeah,
features.
yeah.
So 10 in 0.5, so probably it's a lot of garbage over there.
Correct.
So number of orthogonal components will be not so big.
Yes,
not
yes,
so-
yes. So that's a very valid point. So they also call it as downsampling, what you said as orthogonality. Like you have a lot of these different samples and you try to minimize it so that you can produce. But nowadays, we have systems that can consume all these different features, so you don't need to downsample if there is no need to do that. So earlier days, you had to physically downsample because you didn't have computing power, you didn't have cloud systems, and you wanted to find out, okay, I'll just work with the small sample set. Now you don't have to do that. You can actually work with all the bigger data sets because you have, I'll show you the example, like when I show a demo. If I have time, I'll show you. Yeah, moving forward. So this is how a workflow works for a supervised learning. So you have a data set, you do the feature extraction. Feature extraction is figuring out which features are important from the data set. Then you go build a learning classifier, and you get a training classifier. And that is your training data set, like that training label, right? So this is what it is saying. And once you have built a classifier, you want to validate how well it is performing. And the validation steps comes as follows. So you do some pre-processing, massaging of the data, etc. Then pass it through the train classifier and let it predict. It will come with false positive or false negative, or it will true positive or true negative. These are the only 4 outcomes that it can come with, right? And so that's what I am saying. So you build a class. The first is the training step. The first step is the training. You have your data set, train the model, build the model. So the classifier has been built. Now when the classifier is built, you have this validation step, whether how good this classifier is. That's the validation. You see, it's not much different from both the processes. But the output here is you're predicting how this model is performing, and the first part is actually building the model itself. That's the training process. So a binary classifier could look like something like this. So there are only 2 outcomes, yes or no, true or false, something like that. So there are 2 axes, and what a classifier essentially is doing is trying to draw a line. So if you have a 2-dimensional space, it's just like a line. So anything above this line is true, below this line is false. Or this is positive, this is negative. So now think it for a multi-level classifier, not a binary. It's an n-dimensional plane. So that's just a plane that cuts between the thing and says anything above this dimension is in this category, this dimension is that category. So that's the idea. So this is a 2-dimensional binary classifier. So that's what it is trying to show. Right? Moving next. So this is how you evaluate a model. Right? I already talked about. So you have this actual class, that is the true output, and that is the predictive class, what your classifier has predicted. So you see on the x-axis is the predictive class, on the y-axis you see the true class. And there can be only 2 kind of outcomes, positive or negative, right? And when you have this TP means true positive, false negative, false positive, true negative. So basically true positive is that your predictor, your classifier has predicted is true, and actual result is also true. So this is what you want from your classifier, right? This first thing, like it is actual class is also positive and the outcome is also positive, which is good. However, that's not the case. You can get all these 4 kind of combinations from your model, and that's what you classify. That's what you're trying to find the accuracy, performance, recall of a model. This is how you get how many number of true positives are there, how many numbers of false negatives are there, how many numbers of false positive and true negatives are there. So that's how you evaluate. This is also known as confusion matrix, right? So you're classifying